thank you all for coming. It's a super exciting event for me, and in my experience, it's very rare to go to cross-disciplinary conferences where there are people who actually talk to each other across disciplines, and where there's stuff of genuine interest to everybody in each of 4 disparate fields. And we always thought of game theory as a unifying factor in economics, but mostly that's been potential. Now it's starting to be realized. It's very exciting to have bridges to other fields, and sort of try to have the cross-fertilization that I think is very productive. So let me start by apologizing for the proliferation of logos. The European Research Council, which pays most of my bills, insists on having their brand paraded. So I thought, in all fairness, I would brand everybody who helps me in any way. But in any case, you can see that the work comes from a lot of places. And in fact, I'm ashamed to say I've been working on this paper for 6 years. Now I sort of think it's done. It and the slides are open posted on my website. And the easiest way to get to that, although you can get to it through San Diego or through Oxford, just Google me. I'll be, I think, usually the first thing that comes up under Vince or Vincent Crawford. Go down a few inches and you'll see most of the things prominently posted. It happens that the slides were done slightly later, so the slides differ from the paper mostly in being more accessible as slides are, but also in having a slightly clearer explanation of what the pictures at the end mean than is in the paper. And if you're a referee, I will fix that. If you just say R&R the paper, I will make the paper as good as the slides. It's key in economic theory, anyway, to try to get around and give the seminar in front of all of the referees before the paper is refereed. So that's part of my goal. Okay, so I have to, as the title has already suggested to some of you, the paper revisits a famous paper by Mark and Roger Meyerson, which he spent a lot of time talking about a couple of hours ago, which is going to save me a lot of time. But I just want to say, the goal of behavioral economics in general and behavioral game theory specifically is not to destroy economics, but to improve it. So behavioral economics came out of a partly bad tradition where the goal seemed to be proving that people weren't rational and saying, yeah, your models are no good. Actually, I think what the right goal is, and what a lot of good researchers on the frontier now think the right goal is, trying to redo economic theory with more respectable behavioral assumptions, and in the process trying to resolve some puzzles and do some things that can't be done in a sort of narrow perspective of conventional microeconomics. So if you ask yourself, what is it that's important about strategic microeconomic theory? One of the first things that come to mind is this wonderful paper by Meyerson and Satterthwaite, the E3 jet. And so it's a natural thing to try to improve. It's a thing that today I'm going to try to improve by improving the assumptions about strategic behavior and try to see where the mechanism design problem leads. And it's important paper. As Mark said, it's one of the, he didn't say it was one of the first, but it was one of the first papers where people started thinking of institutions as an endogenous variable that could be optimized rather than a God-given thing to which we were supposed to analyze people's reactions. And I should say, one sign of its importance is it's already generated 1 Nobel Memorial Prize. Since physicists are there, I have to add the memorial, and that's so far. So let's hope that it's worth 2 prizes. But anyway, it's worth at least 1 prize. It's not just another paper. So the key assumption that I'm going to focus on, as Mark said, they assume that, as is standard in microeconomic design theory, that the designer knows that the players or the people that he's designing for will play any desired Bayesian Nash equilibrium in the game created by the chosen mechanism. So that's a standard assumption. That's the assumption I'm going to relax. And what I do is I focus on direct mechanisms, which is sort of necessary for reasons that will become clear later, I hope. and I replaced the equilibrium assumption with a model that is a structural non-equilibrium model that I'll describe in more detail later, which goes by the name level K or cognitive hierarchy model. And these things are, as I'll describe in a moment, these things are supported by a lot of empirical evidence on strategic thinking and people's initial responses to strategic situations. And they don't say that people are always not going to play in equilibrium. They say when people are going to play in equilibrium and when they're going to do something else. So that's also something I'll describe in more detail. And I make everything else standard. So it's usually a good intellectual strategy to change one thing at a time because the interactions between the different things you change are sort of an order of magnitude more complicated. It's not that I think everything else is necessarily standard in the world, but it's just, it's hard enough to do this if you just relax equilibrium. If you relax anything else, you might go crazy before you get the problem done. So anyway, the motivation, which I'll go into a little bit more detail because I think it's quite unfamiliar even to people in my own field, is mechanism design almost by definition creates new games, and it often creates complicated games. And the reason why we assume equilibrium is usually a learning reason, which requires people to have been playing the same game over and over again for a long time, even with different partners. Otherwise, it's a repeated game. You can't learn to play a single repeated game within the play of the repeated game. So it's a strained justification for equilibrium. We think it's okay for many things, but it's somewhat less likely to be okay for mechanism design than it is for other applications of equilibrium, and therefore it's potentially useful to think about what happens if you drop it. I've said that here. So a little bit of subconscious psychology. Why do we assume equilibrium so much? And I do think we overstate the scope of the learning justification for equilibrium. We basically do it for two reasons. Should be able to count them. There are millions of alternative non-equilibrium models, and 20 years ago we had no clue about which of them was right. So if I told you I was going to go do non-equilibrium analysis of Meyerson and Satterthwaite or anything like that, they would have said, what are you going to assume instead? And I would have had no credible basis for making any particular assumption. And the second thing is slightly more subtle intuition. Nash equilibrium is a kind of rational expectations equilibrium. As Mark explained, and I'll explain again because it's important, in Nash equilibrium bundles two things. One, the idea is that individuals choose rationally. And the second is that individuals have the same beliefs about how the game is going to be played. So how could Mark and I have the same beliefs about how a game is going to be played in a game that we're playing de novo without any opportunity to learn from experience how people like Mark and people like I behave in situations like that? Implicitly, what's being assumed is that my brain contains a perfect model of Mark, including a perfect model of Mark's model of me, and so on ad infinitum. And one way I say this glibly is to say our heads aren't big enough for all those models unless they're perfect. And in reality, people don't have perfect models of others. As you'll see, there's a lot of evidence that people's models of others are systematically simpler than their models of themselves in a specific way. And the level K model and cognitive hierarchy model sort of codifies that asymmetry and sophistication. But to go back to the puzzle is Nash equilibrium is a rational expectations equilibrium. We're taught in economics mostly by macro and finance people, so you should take it with a grain of salt maybe. But we're taught in economics that you can't do systematically better than rational expectations. As it happens, it turns out that in this context you can. And I will try to make it clearer later, but it's important, let me say it again. I'm going to argue that fixed point reasoning is not accessible to people. And therefore, if you deny them fixed point reasoning, they have to do something else. And as we'll see, that something else can make models do systematically better than the rational expectations of the Nash equilibrium. So there's an intellectual problem. How can you do better? And the problem, in effect, is solved by cognitive restrictions that are justified by experimental evidence. So let me go ahead. That's where we're going. So a lot of experimental evidence. My frequent co-authors and former students, Miguel Acosta Gomez and Degore Uriberry, and I published a big long paper in the 2013 volume of the Journal of Economic Literature surveying this stuff on strategic thinking and with applications and theory and a summary of the evidence, which I won't go through here, but which in this paper and almost all of my other stuff is on my website, although I think the JEL puts his stuff up for free, even if you don't have a subscription. Maybe that's the Journal of Economics. Well, anyway, it's on my website. You can't find it for free anywhere else. So as I said before, Nash equilibrium often requires fixed point reasoning. If you think of it as the result of strategic thinking, people have to solve a fixed point problem. Or if they don't, often they have to do something like an indefinitely iterated dominance argument. And I'll say one thing, I think Christos Papadimitriou is not here yet, but he proved, among many other interesting things, that makes the problem of computing Nash equilibria NP hard. So I don't want to put too much stress on that. What I do know, though, is if you put people in lab situations where Nash equilibrium involves fixed point reasoning, they never do fixed point reasoning. And they do something else that sometimes mimics the effects of fixed point reasoning and sometimes not. And that's what I'm going to try to lead you to. So questionably, as initial responses, the idea of fixed point reasoning and the idea of indefinitely iterated dominance are behaviorally non-starters. And I want to stress I'm not saying that people can't converge to something in a stationary environment that we need fixed point reasoning to characterize. I'm saying only that fixed point reasoning does not directly characterize what people do. So that's meant to be sugar-coated and less objectionable than the more radical thing you might have thought I was saying. Nonetheless, it still makes a fundamental difference in how you think about using game theory to describe people's initial responses to games, and that's the subject of course of your paper. So, as I said before, if they can't do fixed point reasoning, they have to do something else. I'm going to assume that the something else is not completely irrational, but rather that it relies on simplified models of others, and that's how they get around the difficulty of doing fixed point reasoning. And as I said before, there's a lot of lab evidence surveyed in the JEL paper that shows that they tend to do something which I call level K or cognitive hierarchy reasoning, which I'll describe now in detail. The claim is not that that explains all of how people deviate from equilibrium. Roughly speaking, in a wide variety of situations, I think it explains more than half of the deviations. And I insist that more than half is a hell of a lot. It's much more than I thought 20 years ago. It's not 100%, but if Kahneman were here, I would just say, look, the cup is half full, it's not half empty. It's very surprising that you could explain as much as 50% or more of deviations from equilibrium by any simple model. So the basic idea is level K model, you start by anchoring your beliefs in a naive guess about what the other person or people are going to do. There are some tricky things about generalizing this to n-person games, which I don't have to deal with here because I'm talking about bilateral trading. So let's just think of a single other person. And then you massage your beliefs by a small number, usually empirically 1, 2, or 3, of iterated best responses. Both of those things are cognitively much simpler than doing fixed point reasoning, even in games of asymmetric or incomplete information. You just guess and then you massage, and lab subjects can easily do that if you give them the task of doing that, and they act as if they were doing it, even if you don't give them that task, but rather have them interact against other lab subjects. So it happens that empirically, people typically have different levels. The hope is that you get a stable distribution of these levels in the population. Very roughly speaking, if you had to guess in a typical situation, you might get 50% level ones, maybe 35% level twos, and the rest level threes if there were any. And of course, there's a lot of noise. And in our experience, there are some unclassifiable people, but the proportions among level ones, level twos, and level threes are usually the same. And the important thing is there are very few of anything else. In other words, you can look semi-parametrically or even non-parametrically for other rules that you left out of the model that people were following. And in our 2006 AER paper with Miguel, we basically do that very carefully in a very carefully done set of experiments. And we basically find that there's nobody who really plays equilibrium. There are some people who come close to equilibrium. There's nobody who does anything but level 1, level 2, or level 3. In particular, there are no people who are sophisticated in the sense that if you took somebody like Colin Kammerer and he sneaked in and was your lab subject, so he knows both game theory and behavioral game theory very well, there's nobody who can outguess the mechanical rules that we find in the population either. So very roughly speaking, you can pick up a lot of variation in people's behavior, including deviations from equilibrium, with a model that just has fixed frequencies of level ones, level twos, maybe level threes, maybe equilibrium people. In my analysis today, I'm going to assume that there are fixed frequencies of level ones and level twos. And as you'll see, most of my results are for the homogeneous case where the designer knows that he's facing only level ones or only level twos, because the sorting problems are horrendous, and I'll explain why at the end, time permitting. But that's where we're going. So I've said this. You don't get any level zeros. I think of level zeros when you have an error structure that's flexible enough so that you don't need random level zeros to pick up the randomness. You typically estimate zero frequency of level zero. So I think level zero is not a person. It's a fact about level one's thinking. So in other words, it's just the seed from which level one grows its beliefs, and therefore by extension from which level 2 and level 3 grows their beliefs. That's important here because in mechanism design theory, people typically don't allow decision noise, although one exception, Roberto has a nice paper which I'm going to cite in a while so I don't have to remember the other co-authors now, which does allow noise, and there are a few people who allow noise, but I'm going to rule out noise, basically because that's what Mark and Roger did, and there's no gain to trying to be smarter than Mark and Roger, and it's hard to do that. But anyway, that's where we're going. So I want to point out level K, when K is greater than 0, is decision theoretically rational. What's wrong with it, and the only thing that's wrong with it, is it has a simplified model of other people. And equilibrium would require a model of other people the same as its model of itself. In fact, implicitly it assumes that other people are less sophisticated. And if you're a game theorist, you know concepts that you don't need to know to follow this talk. If you're curious, level K respects K rationalizability. Roughly speaking, the two-person games, that means it survives K rounds of iterated elimination of strictly dominated strategies. So it's not only decision theoretically rational, it's not obviously game theoretically stupid, it's certainly not non-strategic, it's just not equilibrium. And what that means in particular is that if you have a game that happens to be K dominant solvable, namely dominant solvable reducible to a unique prediction in K rounds of iterated elimination, then level K rules will mimic equilibrium rules, not because it's equilibrium, but because they respect K rationalizability. By contrast, if you have a game that's not K dominant solvable, there's no reason why level K rules have to play equilibrium. And in fact, the model predicts what they will do instead, and that's a crucial part of the analysis here. So, I've sort of said that. You can think of it as a refinement of K rationalizability, except that it accepts the heterogeneity of individual levels. So it's not homogeneous the way K rationalizability is. And the key point here is it makes precise predictions once you know the population level frequencies. that makes it a worthy competitor to equilibrium. That makes it not a non-starter to do an analysis like this. And that's, I think, the key point. Here I'm saying that if you want to contrast with other things, some people do mechanism design with things like k-rationalizability. They're cited in the paper, although I think not in the slides. And some people use things like quantum response equilibrium. You can't really do mechanism design successfully with those models because they make vague predictions. And at least we're not yet close to knowing how to do it. And the people who have tried to do it have not gotten very interesting results in other settings. So I'm hoping none of those people are here. I don't think any of those people are here. But in any case, I don't think even they would think of it as an insult. It's just hard to do stuff with k-rationalizability. So they're worthy competitors to equilibrium. And what specific benefits might you hope for from doing an analysis like this? Or since Mark is here, I'll say, you've got this beautiful 1983 paper that's already won its first Nobel Prize. Why mess around with it? What could you possibly get? And one thing you could hope to get is that some of the conclusions actually don't depend on equilibrium, and we'll see examples of that, including the example analysis that Mark did in the uniform case. Another thing is sometimes it'll say equilibrium is wrong, and more specifically, you might have an optimal mechanism, theoretically optimal under the equilibrium assumption, that works only if people play exactly the equilibrium. In other words, that's extremely fragile. And by contrast, there might be another mechanism that does almost as well if people play equilibrium, but also still works if people don't. And we would think that the second mechanism is more likely to be practically optimal because it's more robust. This is one way of formalizing that. We need a way of formalizing that. I think we haven't got any really successful way. And I say later on in the slides, but I'll say now, in case Mark is thinking it for somebody else, the people who do robust mechanism design by trying to get the equilibrium answer under weaker behavioral assumptions, I think are missing it. So I will try to explain to you later, but that's not the right way of thinking of robust mechanism design. Not that everybody who says robust mechanism design thinks that way, but the goal has got to be reconstrued in a way that I'll try to explain later. So I've said that. The final thing is there's a Robert Wilson critique, which some of you are familiar with, not all of you, basically saying we do the theory the way we're used to doing, assuming equilibrium, the optimal mechanism, and on a lot of stuff, including the details of the distribution of private information that real people never pay any attention to. That bugs us because we want the results to tell us something about the world, and the results often look so different from the world. Mark's example analysis of the uniform case, where it turns out that the double auction is optimal, is an exception to that rule, but that actually happens quite a lot. You might hope that the level K model will help with that, basically because the anchoring is exogenous, and so there's a channel by which the answer might be simpler in optimal design. It turns out that doesn't happen. Optimal mechanisms under the level K analysis are just as complicated as they are under equilibrium, though I would argue cognitively simpler for the players to implement. So antecedents, I'll go quickly. Rory and I have a paper that in 2007 Econometrica called Level K Auctions, which is a level K version of Milgram and Weber 82 Econometrica. In other words, a positive analysis of independent private and common value auctions, sealed bid auctions, meaning first and second price, not English or Dutch, not progressive auctions. And we basically show that you can do most of the stuff that they did with the level K model just as well, although somewhat slightly less clearly, I think, than an equilibrium model. We also show that if you go back to the classic auction experiments and you look at subjects' responses in the first few periods, the level K models fit a lot better than equilibrium models or QRE or various other things. So preliminary attempt to do this kind of stuff in a hurry with bunch of my Israeli friends, Tamar Kugler, Zvika Neumann, Adi Pausner, is also interesting and makes a couple of the points that I make here in the context of auctions. By the way, when you see the analysis here, you will see that it's pretty easy to do Meyerson 81 Math of Operations Research Optimal Auctions, and I'm going to do it. Don't you dare do it. I just have to type it up. But this problem is hard. And Renee Saran, a former PhD student of Roberto, if I'm not mistaken, has this wonderful paper on the design problem. Terry Neeland of UCL, formerly of UBC, has a nice analysis of level K implication. Olga Gorokina, who works somewhere in Europe, I forget precisely where, has a very nice level K analysis of the expected externality mechanism. And DeClippel, Saran, and Serrano, Jeffrey DeClippel here. Does he still works here? Well, anyway, it's not. Where is he? Okay, hi. We have to meet. But anyway, they have a very nice analysis of design with bounded depth and reason. But I won't talk more about that. So what am I going to do to you? First, I'm going to do Chatterjee and Samuelson's bilateral trading by a double auction, which Mark already did. So I'm going to go quickly, and you know, most of it's exactly the same, even the same notation. So I was going to apologize to you for changing the notation from your paper with Roger, but I can see that both of us have gotten sufficiently less tolerant of subscripts and superscripts as we age that we converge to the same notation without coordination. But anyway, I'll go through that quickly, and I'll give you an executive summary of Meyerson and Satterthwaite, which is pretty much the same as what Mark said. Later on, I'm going to do it in the level K case, and you'll see that Meyerson and Satterthwaite will be a special case. So in other words, you'll actually get to see a little bit more detail about the methods of proof as a byproduct of the level K version of their analysis. And the next thing I have to do is teach you how to generalize level K models to games with asymmetric information, because the story that I told you before doesn't do that. It's important how you do that. And in fact, there's a sort of neat way of doing that gives you a lot of analytical tractability, and I think captures a lot of the naivete of real people in situations where you have to think about how other people are going to use their private information. Then I'm going to do the double auction, and basically what I will show you there is that level ones are excessively optimistic, makes them excessively aggressive. That would be good for an auction designer who's just trying to pump money out of them, but it's bad for a bargaining designer because the aggression makes them crash a lot more than equilibrium people would. By contrast, level twos are pessimistic and wimpy, and that's good here, although it would be bad for an optimal auction designer. And I don't say it here, but if you went higher, you would basically get moderated versions of the same things, odd and even, alternating. So very roughly speaking, since I'm back in America, I can say level ones are like first term George W. Bush, level twos are like first term Obama's. And in other words, they're sort of a little bit either too unconservative and unconsidering of other people's strategic behavior, or too the opposite. And both of them lead to deviations from equilibrium in opposite directions. And the fact that they deviate in opposite directions make the analysis tricky and interesting. I think it's not the only reason why I think it's interesting. Next thing, and this is radical, there's something called level K menu effects, whereby anchoring on a level 0 and massaging your beliefs a small number of times does not eliminate the effect of the anchoring. And the fact that the anchoring matters and the anchoring is fixed while you change the mechanism means that different mechanisms create different kinds of wrong beliefs. And that actually kills the revelation principle, at least in the strong form, and makes the choice of mechanism non-neutral in a way that doesn't have any counterpart in the equilibrium analysis. And most of my results are for the case where you assume incentive compatibility anyway, adjusted for level K beliefs. But it's a little bit of speculation, and it's already clear from the examples that I'm going to teach you that you can sometimes, in theory, do way better by dropping incentive compatibility. So we'll get back to that. But the revelation principle is not without loss of generality here. You might still want to assume it for reasons that I'll discuss later, but it's really a choice here. Whereas by contrast, in Meyerson, it's adequate in all other equilibrium mechanism design without any special problems. There's no difference in theory between a complicated mechanism and the simplified mechanism, which Mark told the story about. Namely, the designer says, guys, just tell me what your values are, and if it's optimal for you to lie now in this complicated mechanism, I'll lie for you in a direct mechanism. That's not without loss of generality here for reasons that I'll try to illustrate more concretely. So the first step is to characterize mechanisms that are efficient in the set of level K incentive compatible mechanisms for known populations with one level. The punchline briefly is you can do Meyerson and Satterthwaite's analysis for that case pretty completely, and it shows that the stuff that makes a mechanism good for them makes a mechanism good for me, and there's one more thing that's not in an equilibrium analysis that also makes a mechanism good, what I call tacit exploitation of predictably incorrect beliefs. So more on that later. Then what happens briefly if you relax level K incentive compatibility, and what happens if you relax level homogeneity in the population. Those last two things I really can't do. I could tell you why it's hard to do it, but the paper is incomplete in the sense that I can't do it. So let's just go quickly here. And the main point of this is to do Chatterjee and Samuelson's analysis. That's Bill Samuelson. They did the first Bayesian equilibrium analysis of the double auction at a time when we still didn't really know that you could do meaningful equilibrium analyses of games with asymmetric information. And this is mainly a way of familiarizing you with the environment. The notation and the environment are almost exactly the same as what Mark described, so I will go quickly. So basically, quasi-linear von Neumann-Wurzer utility functions, which means people are risk neutral in money. And in the analysis, it also means that any efficient mechanism maximizes the total expected surplus across the two bargainers. That's the key thing. If you didn't have that, there would be subtle and presumably small income effects that would mean that there would be different mechanisms, some of which were skewed in favor of buyer and some of which were skewed in favor of seller. They rightly saw that that wasn't the essence of the problem and that you could make a lot more progress getting rid of that. And that means later on that we'll be able to solve for the efficient mechanism by solving an optimization problem just like theirs with wrong beliefs in it. So same notation, except I make a distinction. The caps are for true values and smalls or small v and c are going to be for reported values. And the usual assumptions here are they're independent, they have positive densities everywhere in their supports, and in the original analyses, the densities could have any bounded overlapping supports, so it could be like this. All the action happens in here. And as Mark did this morning, I'm just going to forget about the outside because the notation is horrible and it doesn't really add any insight. And I say it doesn't involve important loss of generality. It does mean that I have to make a specific assumption about how level 0 is defined later on in the level K analysis. So rules are the same as Mark described. Let's move ahead. Lots of equilibria, linear equilibrium. The key thing about the linear equilibrium is both buyer and seller shade their bids as 2/3 of their values. And that means that they don't always trade when they should. So that's the thing. There's not really an asymmetry here. It looks like an asymmetry, but if you draw the pictures, you'll see that it's actually symmetric in this respect across buyer and seller. And the key thing here is that trade happens if and only if V true value is greater than or equal to C plus 1/4. God would want this 1/4 to be a 0. And the fact that it's 1/4 means that there's that gap that Mark showed us the beautiful picture of. And he didn't do the calculation, but obviously you don't want them to trade more than 50% of the time, because that would involve bad trades as well as good trades. You can ask, how bad is this equilibrium? And it turns out that they trade 20 or 28% of the time, and they get pretty close to the maximized possible surplus, 0.14 rather than 0.17. But anyway, there's still some inefficiency. And as Mark said this morning, that made them ask, well, is this just a problem with the double auction? Is there any feasible mechanism that we could use to get around this problem, still assuming equilibrium, given the mechanism? In other words, still assuming that the mechanism must implicitly or explicitly create the incentives for people to reveal their private information, because the optimal allocation obviously depends on their private information. You could do something constant, independent of their private information, but that's always going to violate individual rationality for some people, and it's also obviously not going to get you close to efficient trade. So Meyerson and Satterthwaite, this is a quick executive summary of what they did. There's going to be a more detailed summary later on as a byproduct of the level K analysis. And again, this is pretty much what Mark said, so I'll go quickly. You've seen that. Direct, you see Mark's definition of a direct revelation mechanism, just something that's conformable to reporting your values. In particular, something like the double auction, even though it's not incentive compatible, is a direct mechanism in the sense that the bids are like value estimates. So I mean direct mechanism to include things like the double auction and any other thing in which people just report numbers that are scalars like the values. And the key thing about the analysis is you can summarize everything under quasi-linearity by two functions of the reported bids, because that's all the designer sees, namely the probability of trade function, P of small v, comma small c, and the expected transfer function. And so incentive compatible, I think you sort of already know what that means, but basically it just means people have the incentive to report the true values, meaning the game created by the mechanism makes it one of possibly many equilibria for people to report their true values. So that's the standard definition of incentive compatibility in equilibrium-based design theory. And we won't have to modify that much. We'll just have to change the beliefs to level K beliefs and basically repeat the definition. Interim individually rational. Interim means after you know your own value, but before you know the outcome. So in other words, it's no fair if the outcome is bad for you, worse for you than you expected. You cannot withdraw at that point. You have to commit to the mechanism when you already know your own value, and the mechanism has to create positive or non-negative expected value for you at that stage. And revelation principle, Mark has said. Here's the quote from the paper, which you can read in the slides, and we've already hit through that. What are the basic results? Their numbering, their theorem 1, basically uses the incentive compatibility and individual rationality conditions to create what I call an incentive budget constraint. And this is my phrase, not theirs, but it is like an incentive budget constraint. In effect, it says you've got to make buyers and sellers happy. You've got to make all of them happy as a function of their values, their privately known values. How happy do you have to make them, and how much is it going to cost? You add that up, and it can't cost more than 0, because you can't import money into the mechanism. So that, then the incentive efficient outcomes, because of quasi-linearity, must maximize the sum of traders' ex-ante expected utilities. Theorem 2 characterizes the outcome functions, the optimal P and X function, and the corollary, which Mark stated this morning, shows that no incentive compatible individually rational mechanism can be ex post efficient with probability 1. And that's true in general, not just in the uniform case that Mark was talking about. And the proof of that is very clever. That's not completely robust, as I'll assert later on. In other words, in theory, in extreme cases, it might be possible for level K mechanisms to beat that, but I don't have any examples of that. So we're going to go into this in more detail later on. So one thing, though, that's important to keep in mind, and this is another thing that Mark said for me, but let's just say it again. If you do the double auction example with uniform value densities, Myerson and Satterthwaite, the theorem 2 actually can be solved for the optimal mechanism in closed form in that case. And this is a miraculous thing that I think is the single thing that most people remember about the paper, namely that you can actually compute the optimal mechanism in closed form, and it becomes the same as the double auction. What that means is that even though the double auction is not incentive compatible, its equilibrium outcome is incentive efficient. What's going on? Equilibrium bidding shades to mimic the effects of the optimal mechanism. And as Mark said this morning, that's a coincidence. He was too modest to say who showed that it was a coincidence. It's a coincidence in the sense that it's true of uniform value densities. It's generically not true for other value densities. So probably we can argue about this, but I think you already agree it doesn't make any sense to obsess about this. But it's an interesting case because you can solve it and because it captures some of the intuition. In particular, it makes the optimal mechanism take a particularly concrete, familiar form, which is what I think Robert Wilson was hoping for, and which the analysis here shows is maybe a quixotic hope, but that's the thing. How do you do level K modeling with asymmetric information? This, I think, is an interesting question in which I think the experimental evidence now comes close to giving a definite answer. So the usual assumption in standard level K analysis is level 0 is uniform random over the other person's feasible decisions. Why should I think that? Well, there are a couple of stories for that. One, you could just think it's the principle of insufficient reason. I think of it more as a person trying to understand the payoff structure and postponing the detailed analysis of the other person's likely strategic response to the payoff structure. So in effect, the other person scans the payoff structure and gives all strategy choices by the other person equal weight. That's like best responding to a uniform random level 0, which is what level 1 does in the model. So that's standard. Now here's the radical part. I want to generalize that with some precedent, but not much, by taking level 0 to still be uniform random, but more radically independent of its own private value. Now, this enrages game theorists because they think of level 0 as a person, and the fact that it's bidding randomly independent of its own private value means that sometimes it's bidding above its value. In other words, it's not respecting simple dominance. The answer is it's not a person. It's not Mark. It's my model of Mark, and I don't know Mark's private information. It's still logically possible for me to go into a complex contingent reasoning pattern saying, what if Mark had a low value? What would he do then? What if he had a high value? People don't do that. That's an empirical question. I'll show you some very strong experimental evidence that people don't do that. There's somewhat weaker, but field evidence that people don't do that. But it's an empirical question. And this is the way the literature seems to be going and resolving that. So this model, then, if you do that, the model does two things at once. It, one, models people's aversion to fixed point reasoning and gives you a specific alternative to that. And two, it models people's aversion to complex contingent reasoning. And at the same time, it gives you a specific model of that. It captures an idea that I call informational naivete. And I'll get to that in a moment, but let me just say, what it means here specifically is Elmont's decisions are taken to be uniform over the range 0, 1, which is where everything happens. But I want to point out what I would have to assume if I allowed bounded overlapping supports is that it's uniform on the overlap. So people can identify the overlap, but they would have to anchor on the overlap. And I think that's a reasonable assumption, but maybe a little bit shakier than in the case where there is where the overlap is everything there is. And then you define the rest of it just as before. So I've said this already, so let's go ahead. History. Famous paper by Milgram and Stokey, which I forget the name of, but I remember what the name people give to their theorem is, or they may have given to their theorem, the no-trade theorem. Basically, it's set in a market equilibrium context. We're going to turn it into a game context in a moment, getting rid of some mysterious aspects of market equilibrium models. And it says what I say there. In other words, you start out in an efficient equilibrium, you give people some new private information, and reopen the market and let them trade again. They can't trade. If they were already at an equilibrium, it cannot be common knowledge that a trade is mutually beneficial. If they made a trade after receiving their private information, that would make it common knowledge that they were both better off, but that's logically impossible. It's not feasible in the model. Therefore, roughly speaking, a trade can't happen in equilibrium because new information is coming in. There are some technicalities. For instance, if there are multiple equilibria and people are partly linear, there can be trivial trades. But the key point of the analysis is this, and that's not why I want to show it to you. It's called the Groucho-Marx theorem because of this wonderful quotation, and it's exactly the game theoretic analog of the kind of reasoning. Groucho was a very smart guy. Some would argue possibly the smartest person named Marx in history. I guess I'm going to be on the internet saying that now. It's going to cause me some trouble. This is an equilibrium inference. It's a simple equilibrium inference, but it's an equilibrium inference. People don't always do that, as I'll show you in a moment. But the key point here in intellectual history is that Milgram and Stokey actually had level 1s and level 2s defined exactly like I do in the paper. And they're called naive behavior and first order sophistication. And interestingly, neither Paul nor Nancy can remember who put them in there, or at least they're not willing to admit which one put them in there. But they're there. And these are, I think, the first clearly specified asymmetric information level K types in the literature. So there's a lot of evidence that this model works well in applications. My paper with Nagore, there's a nice field data paper on movie opening, cold opening, as I say here, by Brown, Cameron, and Laval. There are actually 2 papers by them, one probably in quantitative economics, but this is the more accessible one. And Kammerer et al. Also suggested that you could explain zero-sum betting this way. So zero-sum betting is an interesting phenomenon that I would argue, again, probably on the internet, that it's a lot of what goes on in real asset markets. Basically, people trading things thinking that they're smarter than other people, but they can't both be smarter than other people if they're trading in one direction. And the best quote on this is from Damon Runyon's Guys and Dolls. Actually, the story that it comes from is called The Idol of Miss Sarah Brown. It's worth looking up. Reading the story will teach you that if you've just seen the movie, Sky Masterson's real full name is Obadiah the Sky, meaning a guy who will bet the Sky Masterson. And what this basically says is that Dad is worried that his son is a level 1. In other words, he knows his son is rational. He knows his son likes money. But he's afraid that his son will not draw the correct inference from somebody's willingness to make what looks like a bet that's too good to be true. And we see a lot of examples of this. I'll give you one funny example. A former warden of All Souls College bet a fellow whose study overlooked the Great Quad, which has an oval lawn, that the lawn was more circular than oval. And that's a zero-sum bet, and it's a sucker bet because the warden made the bet knowing full that he was betting with a man who looked down on that lawn every single day, whereas the warden's lodgings don't look down on that lawn. That shouldn't happen in equilibrium. And we'll see a more concrete example of that in a moment. The concrete example comes from a wonderful experimental paper by Isabel Brocas, Juan Carrillo, Colin Kammerer, Stephanie Wong, not the Joseph Wong that Colin also sometimes writes with, that came out in the 2014 RA Stud. And I will walk you through this quickly because I'm a little bit worried about driving out substance, but it's easy to follow in the notes. But here's the setting. The setting is there are three ex-ante equally likely states, column A, B, and C. And the information structure is player one privately learns either that the state is A or B, or that it's C, as in the partition. Player two learns something overlapping but different. So collectively, they know exactly what's happened, but the information is dispersed. And the question is, can they bet on that? The rules of betting are you observe what you observe about the state. Then you say bet or pass. Saying bet expresses a willingness to make a bet, which results in a bet only if the other person also says bet. Saying pass unilaterally guarantees that there's not going to be a bet no matter what the other person says. If there's no bet, you get a 10, which is somewhere in the middle range there. So you can do an equilibrium analysis of this, and I walk you through it here. I did these slides first before Christmas, but I still think red and green is a good color for this. And you can show that there's no betting in any state. In one state, state C, player one is willing to bet, but it doesn't work because player two is never willing to bet at the same time that player one is willing to bet. And that's an implementation of the no trade theorem without any of the magical stuff about auctioneers and markets and things like that. Nonetheless, people do bet a lot. And roughly half of the subjects bet, not just because of boredom, because they're making a lot of money or losing a lot of money when they bet. And the pattern of betting varies systematically with player role and state. And you can analyze this from a level K point of view, looking at the behavior of level ones, level twos, and level threes. Level threes mimic equilibrium here because the game is actually three dominant solvable. I didn't walk you through the equilibrium argument, but if you look through it later, you'll see that. And it turns out that they non-parametrically estimate a bunch of clusters of subjects clustered by behavior. And there's a cluster that looks exactly like level one people, a cluster that looks exactly like level three people, and a cluster that sort of looks like level two people. But it's not structural. They're just saying, let's just look at what people do and see if they group in any natural way, and they endogenously get these level K people. And more remarkably, although I may have forgotten to say it in the slides, or not said it in the slides, they actually estimate people's information searches, as we sometimes do in this literature, like in my 2006 AER paper and my 2001 econometric paper. And information searches also cluster in the same way. So there's very powerful evidence that what's going on is this level K model with at most 3 levels, and that's what explaining both why people bet despite the equilibrium no betting theorem, and when and where people bet. So I think there's a lot of pretty good evidence for this model. In any case, I'm going to assume this model. Now let me go very quickly about this. Let me just give you the executive summary of this, because this is the analog of Chatterjee and Samuelson's equilibrium analysis with level K people. I'm going to do 2 cases here. One where a level 1 plays against the level 1. Another where a level 2 plays against the level 2. But remember, when a level 1 plays against a level 1 model the other person is level 0, not level 1. That's what I meant when I said people act as if they thought they were smarter than other people. And similarly, when a level 2 plays against a level 2, his model the other person is the other person's level 1. So it's just algebra, so let me just give you the executive summary. In the uniform case for level 2s, and in any case for level 1s, the optimal bidding rules are linear and the shading factor is still 2/3. So just as in the equilibrium analysis, people shade their bits by a factor of 2/3. But the gap, the trading gap, varies systematically with level. And in particular, what it does is it justifies what I said before about Bush and Obama. In other words, the constant terms in the bidding rules make level ones more aggressive relative to equilibrium than they should be, and level twos less aggressive. And when you put the bidding rules together to figure out when they actually trade as a function of their true values, that means the gaps are ranked in that way too. So it's just it's a coincidence, at least in the level 2 case, that you get that. But it means that there's a well-defined sense in which level influences the efficiency of the outcome. In other words, the trading regions are all going to be nested for this mechanism. So that's really all you need to know about that analysis. But what should it make you think? It should make you think something analogous to what Roger and Mark thought, namely, is it just the double auction or is it a problem for any mechanism? But let me refine it a little bit. Suppose you knew you had level ones. They're aggressive and they crash all the time. Is there any way to design a mechanism to cool off these hotheads and get better outcomes? And the answer is, if you're willing to assume level 1 incentive compatibility, yes. By contrast, level 2s are wimpy, and wimpiness is good. Can you design, well, we already sort of know from the Saturday and Samuelson analysis that you can design a mechanism that mobilizes that wimpiness to get better than the equilibrium bargaining outcomes. The double auction does that. Actually, you can do even better than that with something like reserve prices. So that's the motivation of the level K analysis in more detail. And now we're going to fast forward ahead. All of this stuff is in the slides if you want to see the details. But the details are not essential for my purposes, and I don't want to write something that is essential. So how do you do mechanism design for level K bilateral trading? I have to restrict attention to direct mechanisms for a couple of reasons. One of which, I think the most important one, is we don't have enough evidence on which to base a credible specification of a level K model for more complex mechanisms. Now, you can, my colleague and co-author Joel Sobel thinks that that's a damning criticism, although he's not against publishing papers that can be subject to damning criticisms. But he says, you're not really showing that these things are optimal. You're showing that these things are optimal in the subset of models that you can characterize. But anyway, I personally think it's progress. It's something that allows you to see stuff that you couldn't see before, and maybe somebody will find a way to specify reasonable models for non-direct mechanisms. And I also think that it's pretty hard to imagine something other than a direct mechanism being used in applications. They have to be pretty simple, and direct mechanisms are the most obvious way of making things simple. And I focus on mostly on homogeneous populations, but certainly on populations of level 1s and level 2s. And as I said before, I ignore the noisiness of decisions. Everybody else does that, except Roberto. Why shouldn't I do that? It's hard enough. And the thing is, incentive efficiency notions are defined for correct beliefs. In other words, the designer knows the situation. He knows the mix of bargainers, traders that he's facing, and he also knows what they're going to do because he has the model of what they're going to do. So he maximizes the same kind of objective function. The difference from Meyerson and Satterthwaite comes in the constraints. The incentive constraints are different only because they have non-equilibrium beliefs in them they have level K beliefs in them instead of equilibrium beliefs. And that means that only the incentive budget constraint and the individual rationality constraints are going to change. So that allows you to do some stuff that I originally thought maybe you couldn't do, at least in the homogeneous case. The incentive constraints become more complicated in the case of heterogeneous levels because then I have to screen levels. And I can't see how to do that. And I've talked to everybody who knows how to screen more than one thing at a time in the world. None of them can see it either. But if you can see it, I'll give you a good lunch or a good dinner in Oxford or whatever you want. I mean, I really want to know how to do this, but this is what I can do. So that, I use the phrase incentive compatible in the narrow sense, meaning that people have to report truthfully. Some people like to use it in a broader sense, meaning that when I choose a mechanism, people choose an equilibrium response to it, or at least the best response to it. But I use it in a narrow sense. And I still assume that people best respond, even when we're not using it. I've said this, and the terminology is pretty obvious. And one question is, which I'll also give you an executive summary of, because I want to get to the pictures. Should we assume level K incentive compatibility? Because it's not without theoretical loss of generality anymore. The double auction is not level K incentive compatible, but for level 2s, if you knew you had level 2s, it can give you a lot better outcomes. People are of two minds about this. The school choice designer people think incentive compatibility is essential. You shouldn't drop it for anything. Some of the auction people, including the modern mailroom, think that you shouldn't drop it. They're thinking about complex combinatorial auctions, and they've come around to the belief that you need it, even despite the revelation principle. However, it must be said that they're not thinking about situations where there's even any theoretical advantage to dropping it. They're all assuming equilibrium or something like equilibrium. So maybe they don't have considered positions on this. In any case, what happens is I have very clear results in some cases when you assume it, and just stories when you relax it. So I'm going to focus on what happens when you assume it, and why does it happen? That's what I just said. Well, I'll tell you why it happens when it comes up in the slide, because that's probably the optimal time to tell you. So what Meyerson and Satterthwaite did in the corollary, this is just a reminder of what they did, which you've seen recently enough. And this is a reminder of the result for the uniform value densities that says the optimal mechanism is equivalent to the symmetric double auction. And that's still true here in the uniform density case. That's one example where the equilibrium analysis is completely robust to level K thinking. And the reason, it's a coincidence, as the original result is, but for a different reason. The reason is that level 1s accidentally have the right beliefs, because they assume uniformity. In this case, uniformity is true. And if they're incentivized, then level 2s have the right beliefs. So the designer doesn't even need to know the mixture. As long as he knows he's got only level 1s, level 2s, and level 3s, and so on and so forth, he knows that the double auction is still optimal. So that's an example, sort of a trivial example of robustness. There's a story here about menu effects, and I think it's an important story, but the basic punchline of this, and you can read it in more detail, is that even if you fix level 0 anchoring on 0, 1, and then you consider moving the mechanism around. Moving the mechanism around moves equilibrium beliefs around. And for level 1s, it leaves level 1 beliefs fixed. Therefore, the wrongness of level 1 beliefs is a function of the mechanism. It's not neutral anymore. That's why the revelation principle fails. And I say this in more detail here. And we've already seen this in Chatterjee and Samuelson examples. Theorem A shows that you can cool off level 1 hotheads. All you have to do is run the direct incentive compatible version of the Meyerson and Satterthwaite optimal mechanism for uniform beliefs. You cannot run the double auction because then there'll be hotheads. But the Meyerson and Satterthwaite direct incentive compatible version cools them off, makes their beliefs correct. And by contrast, the double auction leaves the level 2s wimpy, which is good. So in other words, you want to do something very different in opposite directions, the level 1s and level 2s. I say that here, and I mean, equilibrium gets rid of these menu effects because even if you anchor, if you eventually reason your way to the equilibrium is independent of the anchoring. But for finite numbers of massagings, you don't get rid of that. So let me just say this once again. I'm not sure I have enough time to really do this, but let me just give you a slightly more detailed summary of the proof of Meyerson and Satterthwaite's main result. What they do is they first calculate exactly how much you need to pay buyers and sellers as functions of their values to create the incentives for them, one, to reveal their values, and two, to be willing to sign up for the mechanism at the interim stage. I think of this as a Jim Muirley's trick from the unreadable 69 optimal tax paper, which got him the Nobel Prize. But anyway, whoever thought of it first, the basic idea is to write these incentive constraints this way and the individual rationality constraints this way. And let me see, skip something. No, later, it'll be later on. This is their theorem. Well, let me go ahead and show you. Basically, what you get by integrating, by using a limiting argument and integrating, is you can write how much you have to pay a buyer as a function of his true value this way, as a function of an integral of the probability of trade function. And same thing for the seller. When you add those two things together, you get what I called an incentive budget constraint, which is this 6.5. And you get essentially Meyerson and Satterthwaite's theorem 1. The difference is this has level K beliefs divided by true beliefs in these bracket terms. In an equilibrium, these things would be 1s. And you would get exactly Meyerson and Satterthwaite's theorem. Same thing down here. They also enter the budget constraint. Well, for this reason. So in that sense, it's an algebraic generalization of Meyerson and Satterthwaite, even though the level K model isn't, strictly speaking, a generalization of equilibrium. But if you think of it as a function of the beliefs and how wrong they are, you get a generalization. And there, when I went back to stuff, that's, I think, the proof is the same. Let me just tell you what the result means. Well, the proof is a bunch of horrible algebra. I can't believe they did it, but it's hard enough to copy, let alone do it originally. Got a lot of integration by parts in it and some changes in variables, but you can do it because the only thing that's changed is you've got level K instead of equilibrium beliefs, and level K beliefs are predictable, and they decouple across people. So the revelation principle makes beliefs decouple because, in effect, each person is assuming that the other person is telling the truth. So even though it's a fixed point problem, you can calculate it by two separate optimization problems. Here, level K beliefs just decouple. So even if the revelation principle fails, you still get two separate problems. Technical aside, forget that. It made no sense to you. The transfer function is basically copied from them, and it still works basically because it doesn't need to work perfectly. It just needs to work for the lowest people and be increasing. Theorem C is the one that actually characterizes the optimal trading function. And here is a little bit different. I mean, the idea is the same as theirs. Basically, write the Kuhn-Tucker conditions and solve for the optimal trading function. But the criterion is a little bit different. My criterion, again, has these wrong beliefs in it. If the wrong beliefs were correct, a little bit of algebra would reduce this to their criterion. You'd basically start by trading on the highest this minus this things. It's like a consumer's budget problem with a continuum of goods, where each good has a price, and each good has something like a marginal utility, and you've got a budget. Because there's a continuum of goods, the budget constraint's always going to be satisfied exactly. What do? You start by grabbing the things that have the highest marginal utility to price ratio. Those are the P of V and C things that you trade on first. And you keep buying them until you run out of incentive budget. And so the solution is bang bang in the sense that the optimal P's are either 0 or 1. And the budget constraint, as I said, is satisfied exactly. One wrinkle, though, is that some of the prices are negative. And that's, I think, also true in Mark and Roger's analysis, although it makes less of a difference there. And you would worry about that, except that the logic of the incentive constraints means that there's no free disposal. So it doesn't matter that the things are negative. If they have negative marginal utilities and you get paid to take them, as long as the marginal utilities aren't too negative, it's still a good deal. So the characterization works equally in those cases. And what happens is you get a criterion. Basically, you pick the highest, the things that have the highest of this. If this thing is suitably monotonic, then this gives you necessary and sufficient conditions for the optimum. What does it mean for this thing to be monotonic? Well, it means essentially almost the same thing that it meant for this thing to be monotonic for Mark and Roger. But of course, the belief being wrong means the condition isn't exactly the same. But it's not true everywhere. It's, roughly speaking, true most of the time. And that's what you can do. So what does this mean for mechanism design? I've said properties. Well, basically what it means is that the wrong beliefs, in effect, make the prices different. So it makes trading on some P of V and C combinations cheaper and some more expensive. And so you shift in that direction. Other than that, it basically means that any property of a mechanism that makes a mechanism good for Meyerson and Satterthwaite also makes a mechanism good for level K people. But with different weights because of the different level K beliefs in the budget constraint. Finally, it means something new. I hope well, I'll say that in a moment, but let me just say, as I said before, corollary one, which is the argument that nothing can be ex post efficient with probability one, you can't push the proof through here. I can't find a counterexample, but the way in which you can't push the proof through suggests that corollary one isn't completely true here. Basically, the beliefs can be wrong enough so that people can be fooled sometimes into trading all the time in extreme cases. But the second thing, and I think the most important thing out of this analysis, is that unless a mechanism happens to induce correct beliefs, the optimal mechanism always has to exploit something I call tepid, for tacit exploitation of predictably incorrect beliefs. Now, my econometrician friends tell me that unless you have a good acronym, your idea is dead. And this is the best I can do with this one. I was a colleague of Rob Engel for a long time who got a lot of mileage out of choosing good acronyms for econometric techniques. But anyway, the point is, it's tacit in the sense that the designer just presents the mechanism to people and lets them think about it. He does not actively deceive them. It's predictable, predictably incorrect, because the level K model tells the designer how people are going to react to the mechanism. And it's exploitation in a design sense, in the sense that he's using their incorrect beliefs to help them, which would be the opposite of what would happen in optimal auction design, where you would use the incorrect beliefs to get more money out of them. So in that sense, it's benign, but it's still exploitation. I can't find a word in English for benign exploitation. I want it to be one word, although maybe two words would give me a better outcome. Here's a point on design, which I mentioned before. Well, a couple of points on design. In the budget constraints, you have to pay people more if they're more optimistic. So imagine if you could give them a drug that would make them more optimistic, or that would make them more pessimistic. Then you would have to pay them less. And in the analysis, you could use the extra surplus to subsidize more trade and make them better off. You can't actually do that. And in the pictures I'm going to show you, what you can do that mimics that to some extent is changing the truth while holding level K beliefs fixed in a way that makes them more optimistic or more pessimistic. And when you do that, the pictures show that sometimes the pessimism effect dominates, that sometimes the effect of changing the truth on the objective function outweighs that. So that's something that's explained better in the slides than it is in the paper. But that gives you an idea of what it is that determines how well you do in the optimal mechanism here. Basically, the incentive budget constraint likes pessimism and hates optimism. So it's like, anyway, that I've said, that I've mostly said. Let me give you one more example. The cheap shot I made against robust mechanism design. If you start thinking about this for a while, you think, well, robust mechanism design, suppose it means, people aren't going to play equilibrium, but they're going to do something. I like the equilibrium optimum outcome. Let's try to get that for everybody. That suggests an auction design that you're going to like a second price auction. But I would argue that if you have level ones, you're going to like a first price auction better, because a first price auction gives them wrong beliefs, makes them bid too aggressively, whereas a second price auction simply mimics the equilibrium outcome. So you have to think of robust mechanism design in a somewhat more subtle way than the simple-minded way that I just caricatured. And I stress, not all people who use the phrase robust mechanism design make this mistake, but I think it's an important point. I want to emphasize anyway. One thing that's surprising and interesting is sometimes, as we'll see in the pictures, you get ex post perverse trade. It's optimal for people to commit to mechanisms that sometimes force them to trade when V is less than C. And that's different from the equilibrium analysis. They don't even bother remarking that because it comes so obviously, and I think you never thought that anybody would want to do that. But sometimes it's optimal for Meyerson and Satterthwaite to have a transfer function that violates ex post individual rationality. This is a different, less subtle violation of ex post individual rationality that's about actual trading, and we'll see examples of that in the pictures. So let me just skip this stuff and get to the pictures. These sections, no, actually, this is what I want to skip is the two sections at the end that say, what happens if there are different levels in the population, how do you screen them, and what happens if you drop incentive compatibility? And the answer is, it's terrible, you can't really do anything, and I can show you why you can't really do anything, but it's not as interesting as this. So what I did was, you could solve for the closed form for the optimal mechanism exactly in the uniform case, just as Meyerson and Satterthwaite could, but you're out of business in all the other cases, just as Meyerson and Satterthwaite were. So we computed them. I don't know if it'll impress the computer science folks, but it took a long time in the laptop, like a week, which is a lot of time for me to do computer computations. In any case, we show you some trading regions. Let me just walk you through them. We can do this only for level ones because there's two-way recursion for level twos in the sense that the mechanism has feedback on level two's beliefs about level ones, and it's too high dimensional for current state of computing. But we can do them for level ones, and it shows something. Here is the case you can solve, and the pictures mercifully are oriented exactly the same as Mark's pictures were, but with worse colors. And nothing surprising there. Mechanisms, roughly speaking, are similar to equilibrium incentive efficient mechanisms. Here are some other cases. First, the point I want to make is the trading regions aren't symmetric. In other words, if you flip the buyer and seller's distribution, you don't flip the distribution. That's because they don't always trade when they should. So there's some history dependence in the sense that the person who starts out with the object is more likely to end up with it. So that's something that is obvious, but it took me a hell of a long time to see that. So I reported to you here so that your life will be a week longer now. In any case, that's an example. Some other ones, L1 buyer's optimism about the seller makes the trading region for L1 smaller. So here are the L1 trading regions. Here are the densities. These are all linear densities. they vary in optimism and pessimism relative to the truth. The truth is always going to be uniform in these examples, and varying the true densities relative to L1's uniform beliefs makes them optimistic or pessimistic. And you can see that a lot of things can happen. For one thing, optimism is bad in these cases. It's not always bad. Optimism for sellers is bad, not equally bad, but still bad in the sense that it shrinks the trading regions. Sometimes pessimism makes the trading region larger, usually. Sellers' pessimism makes the trading regions larger, usually, not always. Sometimes sellers' pessimism yields small parts at high values and cost for buyer and seller of ex post irrational trade. And these are the only two cases of that I found. Doesn't happen a lot, but it does happen in the optimal mechanism, and somehow the reason why it happens in the optimal mechanism is that committing to do this more than pays itself back in making the incentive constraints more relaxed. So I don't precisely have better intuition about that, but it does come out of the calculations. And if you could see these things more closely, not on the picture, but if you had a computer and you could blow them up, this is really flat. It doesn't come down again. If it came down again, it wouldn't qualify as a true solution to the problem because it would violate the analog of the second order conditions. So here, optimism, pessimism, intuition fails basically because shifting the truth shifts the objective function more than enough to outweigh the intuition that comes from the incentive constraints. So the effect is still there. And it's not true that they uniformly always either set contain in one direction or the other. Sometimes they overlap. That doesn't mean that it's not better for people. It just means the trading regions are not set ranked in the way that you might have hoped and in the way that they sometimes are. So I think I want to stop here, just leave out the remaining two sections. Thank you. Really needed an hour and a half, but you could do this in an hour, but you wouldn't, your brains would hurt.
Time for a couple of questions?
Sure, certainly.
I have one actually on the term you said there's no English word for benign exploitation.
Yes.
I wonder whether I mean, there may be many more nuances to what you want to capture, but is paternalism close to what you have in mind?
Paternalism is close, but it's a buzzword from behavioral economics that I don't want to mimic. I actually kind of, in Oxford, searched the world for these words by asking students from all parts of the world, hoping to find such a word in Thailand, but failed. But paternalism, I mean, mechanism, all mechanism design is paternalism. I'm saying, you know, there's an asymmetry between the designer who gets to play God and choose the rules, and we don't really know. I mean, the idea of optimal mechanism design maybe isn't even well posed when mechanisms have to evolve. And we know that there are going to be multiple equilibria, so there's no sense in which what evolves and remains stable is going to be optimal in any sense. But paternalism doesn't quite capture it for me. Mark?
Now, this is pretty new. How does it with experiments?
Everybody asks that. The experiments are much more interesting than my theory, even your theory. The state-of-the-art experiments is something I think that Bazerman and a few other people, Valley, did a long time ago, or people like Radner and Schotter. And the most interesting ones are the Bazerman of all ones. And what they do is they compare the straight double auction, with the double auction preceded by pre-play communication. First abstract through the computer, then face-to-face. And they actually analyze the behavior of dyads. There's a companion paper published in some obscure place that I can help you find if you need it when I'm home. But what they find, and the first point I want to make is, our models in theory cover that, because it's, your model is supposed to be about any possible game. So cheap talk communication is not ruled out. And of course, there's no role for face-to-face communication. But what happens is people reliably get outside the Meyerson and Satterthwaite frontier, even in the double auction without communication, more in the double auction with abstract pre-play communication, and way more with face-to-face communication. And one thing that I think is happening, but not all of what's happening, is in the last case, people actually can incredibly commit to a certain extent not to lie. So the incentive constraints, as you and I characterize them, are not really the incentive constraints, if you could credibly commit. But in their analysis, they show that there's a lot of coordination. So somehow they can sort of coordinate on things like saying, my value is pretty high, let's try for an equilibrium that looks like this. And they talk, and somehow they find a combination that actually exhausts the surplus and ensures a trade. So I think theoretically that's almost as hard to analyze as the dynamic double auctions that you guys are thinking about. And I also think you would want to redo the experiments, because these were done like 20 years ago. We know a lot more. I don't mean to denigrate the experiments; they're fantastic experiments. But we know a lot more about how to do experiments, and it might be that the results are different. Colin Kemmerer has been doing some stuff that's sort of like this, but it's not right on target. We might do something like this. But I'm deeply worried that it'll take us very far away from anything we can theoretically analyze. Nonetheless, it's super important. So you have to choose, whether it's something you probably can do or something that's truly important that you can't do. Good question. Yes?
So as a computer scientist, my understanding is quite limited to kind of big thing of looking through the boundary rationale. So I'm going to ask a question. Level 1 and level 2. Fascinating. Optimism and aggressivity push. Level 2.
Yeah.
Pessimism and win is in some way dominating the other. I didn't understand it.
Well, the effect is context specific. So I should have emphasized, it's not that these people are always going to be too aggressive. It's a function of the game. The easiest way to think of this is to look at, say, Cameron, Ho, and Chong talk about some entry games, which are like asymmetric battle of the sexes games that Kahneman ran and was puzzled by the results of. And you could design these things by manipulating the asymmetry so that the level 1s will come in and therefore the level 2s will stay out. Or for a different game, vice versa. So it's not universal. The point of the model is it tells you who's going to do what, and therefore gives you something that you can calibrate outcomes against. And the mystery, which I think is very interesting, is in these games, the equilibrium-based norm is how well do people do in the best symmetric equilibrium, which is a mixed strategy equilibrium. What happens in the lab is people robustly do better than that. So how do they do that? The way they do that is linked to the heterogeneity of the population and the asymmetry of thinking that I talked about. Suppose you had only level 1s and level 2s and it's 50-50. When a level 2 plays against the level 2, and it's the kind of game where level 2s come in, they crash, so you don't do any better than the equilibrium analysis. The same thing for level 1. But when a level 2 happens to play a level 1, and remember that happens roughly half the time, in effect, the level 1 becomes a stackable leader, and the level 2 can be a follower. So there's action at a distance, something, in the sense that even though the choices are simultaneous, the asymmetry of strategic thinking allows them to break the symmetry just as needed for efficiency.
So it's 50/50, the one.
Well, just say, so whatever the distribution is, half the time you're gonna do no better, and half the time you're gonna do better. And you do better because the asymmetry of thinking mimics the effect of time-synchronized choice. And time-synchronized choice is a panacea for entry games. You never get bad outcomes if people go first and second. So anyway, they did a lot of cool experiments with entry games with more than 2 players and varying the payoffs so that you can actually tell whether it's a level K model that's predicting the main patterns. And Colin, I think he has more information on this on his publicly available behavioral game theory slides than anything he's published. But anyway, I did some stuff like this too from a different point of view. It's on my website under the title Let's Talk, which I've never gotten around to publishing. But I mean, well, I don't know. I mean, so the key point is it's context dependent, but like Nash equilibrium, the level K model transfers across contexts. It gives you a way of thinking about new situations.
So just, I'm coming at this from a computational point of view, and it seems like in these experiments with coordination that you're talking about, that in some sense, having face-to-face discussion allows people to change the priors on the L0. And so in some sense, you're freeing up resources for an added layer of recursion.
I'm not sure of that characterization. The mechanism by which communication seems to change outcomes doesn't look like that.
Okay.
So you need to find the Bazerman Valley and a couple of other people thing, and find the one that's published in some conference volume somewhere that has the word dyadic in the title. There shouldn't be too many things with both Bazerman and dyadic. And you'll see that the patterns are very complex. They're not completely equilibrium patterns. Neither are they obviously level K patterns for any level 0. So.
I was worrying about the stability of the K level. So from what I understood, you have to know the distribution of the types.
Yeah.
Between error types. This additional information that allows you to have this adjustment. But my question is, if the stakes are higher, we modify the K level. That's of course a projection. It's an empirical question.
Yeah.
So
there's relatively little evidence on that. There are 2 questions, I think, that I'd like you to consider. One is transfer from one kind of game to another kind of game. So if you're a level 1 in one kind of game, are you still a level 1 in another kind of game? Or more generally, if 2 people are ranked with a higher or lower level in one game, is the ranking preserved? And that question has been addressed experimentally to some extent by people like Georgianis, Sotiros, and Rob Weber. And I think the results are controversial and not completely supportive of what I'm saying. The second thing is, play things over and over again. Does the level go up? There's a little bit of evidence that it does. I personally think it doesn't go up forever, and in complex games it might not go up at all. So in our own experiments in 2006 AER, 2001 kind of Epica, for one, we don't get feedback, but sometimes occasionally it goes up because people have not forehead learning. But you can test the first half and second half, and there are no significant differences. We don't really know how to do this for dynamic settings. So, but mechanism design by formulation is static. So if we could do it for dynamic mechanisms, it would be very interesting, and we could then, it wouldn't be true anymore, presumably, that the optimal dynamic mechanism can be mimicked by a static mechanism. So there's a lot of interesting stuff to to do there. One more thing to say, but I forgot it, so it's very important. Yes, go ahead.
I'll ask a question. So if I were to think in security markets that more sophisticated strategic thinking should pay, level K plus one ought to do better on average than level K.
Yeah, I don't believe that that's true.
That's my question.
So, one, I mean, I don't completely know how to model those things totally as games, but in other games, you can easily find cases where it's just as bad to be too much more sophisticated than other people as it is to be too much less sophisticated than other people. The best paper I know that will help you think about this is by my former student, Ricardo Serrano Padial, who is moving from Wisconsin to somewhere soon, and it's in JET. And what he does is the following. He takes a standard financial market, although he calls it a prediction market. I think you may have gotten over that. He has two kinds of traders. He has fully rational traders who, and effectively noise traders. What the noise traders do, however, is they follow a mechanical rule that doesn't solve fixed point reasoning. So he doesn't use the level K terminology. But basically, the noise traders are people who respond to the market without doing fixed point reasoning. And the sophisticated traders know that the noise traders are there. They know how many of them there are and what they're going to do. And then they go to a full Sandy Grossman style rational expectations equilibrium in the market. So what Ricardo finds is that in the space of possible realizations of private information variables, the regions where noise traders trade do not coincide with the regions where sophisticated traders trade. They overlap. And to some extent, the presence of sophisticated traders exploits the noise traders, but it also protects the noise traders from themselves. And this effect is similar to something I found in my 2003 AER paper, the one called Lying for Strategic Advantage, which is Crawford and Sobel meets level K about intentions. There you have a mixed strategy equilibrium in which stupid people and smart people coexist. The smart people exploit the stupid people. They try to. But if there are too many smart people, they coexist, and what really happens in the mixed strategy equilibrium is that the smart people protect the stupid people from their stupidity. It's a little bit surprising, but obvious if you know the logic of mixed strategy equilibrium, but it's surprising that it plays out in this way. That's like what Ricardo finds. Although again, I'm not sure he frames it that way, but it's basically happening for the same reasons. So I don't really know where the next step is. I would like to see, one thing I think is wrong with finance is they're too happy to write off non-rational, non-fully rational traders as noise traders and not to bother about modeling them. I think what they do matters, and I think they might learn something interesting by modeling them more explicitly. And the other thing I know is, Ricardo's paper I think is wonderful. He had a hell of a time getting it published. People either couldn't see what was new about it or whatever, but he finally got it published in JET. And I think there's a lot of work to be done in that direction.